All right. All right, so we're just going to go through the classwork from today, and then I'm going to talk about some of the things that I've been writing for the notes that'll be pertinent for Wednesday. So the first question from the notes, the first question from the work today, and I have new chalk. I remember to get new chalk. It says that you have some electron moving to the right, some velocity v. This is a minus q, and there's some electric field given by E vector that's pointing up. And what we want to do is we want to find what magnetic field do we need to apply here in order for the charge to move through this region without being deflected. And so the equation that's going to be helpful for this question is the Lorentz Force Law. And so this says that F vector is equal to Q times E vector plus Q times V cross B vector. Okay. So what does it mean for this to move through undeflected? Well, it means that the sum of the forces acting on this particle is 0. Okay. So that's to say that my electric force is going to point down. So this is the electric force Fe. Because the electric field points up, but we have a negative charge. And that means in order for this to be balanced so that there's no net force here, the magnetic force Fb has to be pointing up. Okay? So what that says immediately is that this equation is equal to 0. And if I treat everything here just as a magnitude that says or look at this, I'm playing around with the way that you would do the negative signs here, but ultimately I'm going to try to use this diagram here. So the sum of the forces is going to be equal to Fb minus Fe, which is equal to 0. And so that says that Fb as a magnitude is equal to Fe as a magnitude. And so that's just to say that QVB is going to be equal to Q times E. I can cancel my Q's, and so the magnitude of the magnetic field is just going to be equal to E divided by V. Okay. Now I want to pause here for a second and talk about notation, because I was going through what some people had done in class today. And some people wrote something like B vector is equal to E vector divided by V vector. Now this is this makes me cry a little bit. And it's not really your fault. You guys don't know any better. You had teachers that said things like this are okay. But what I'm saying here is this vector B is equal to the ratio of the vector E divided by the vector V. And if you're okay with this, then I would go a step further and say, well, what happens if I write this in components? Say that all of these have components in x and y, and so that would be saying like bx x hat plus by y hat is equal to ex x hat plus ey y hat divided by vx x hat plus vy y hat, right? And so you can see, now that I've expanded this a little bit more, the real problem here. If I was to try to plug numbers into this, how would I do that? I have this ratio of E vector to V vector is equal to B vector. This actually doesn't make any sense. And so that's why when I did this step over here, what I did was I got rid of the vector information when I did this. And what I'm really doing here is I'm saying that if this is the y direction, it's the sum of forces in y that I'm dealing with here. So that actually already takes care of my vector. So everything over here is just some magnitude. So I have Fb minus Fe and just as magnitudes. And so this says that B is equal to E divided by V. Okay. So part of the reason why you might have had this one over here is because you realize that you need some vector information to come out of this, because I need to know both what the magnitude of the magnetic field is and what the direction it points is. And so in order to do that, we're going to apply the right-hand rule. So we know that F sub B is equal to Q V cross B. And so really this is Q V B sine of theta times n hat. Sine of theta is going to be 1 because the angle between the velocity and the magnetic field is 90 degrees. And so really the vector information is going to come from this n hat. And so what we need to do is we need to kind of reverse engineer the right-hand rule here. And that's to say I know what the direction of the magnetic force is and I know what the direction of the velocity is. I just need to find what the direction of the magnetic field is. And so the way that we've been applying the right-hand rule is to say, point our fingers in the direction of the first vector, curl into the direction of the second vector, that's going to give me the third vector. But here I actually don't know the second vector. I know what the direction my fingers should point, because that's the first vector. And I know what direction my thumb should point. That's the second vector. And so in this case, I have my fingers of my right hand, and they're pointing in the direction of V. And my thumb needs to point in the direction of the force. So in order to do that, I have to hold my hand like this, and now curl my fingers this way. And so when I'm curling my fingers, it's going to go into the board like this. So this is going to go in this direction. And if Eric's here, I realized later that I had made a mistake when I was explaining something to you. This actually isn't the direction the magnetic field points, because this is a negative charge. So this negative sign is going to carry over and flip the direction of this. And so really the direction of the magnetic field in the end is going to be pointing out. So now I can make this a vector. I say the vector B is going to be its magnitude times the direction that it points. That's how we're getting our vector in here. Can I explain how you know FV is pointing up perpendicular to the V? Yeah. That's because in the statement of the problem, what I wanted was for this particle to move through undeflected. And what does it mean when I say undeflected? It means that the sum of the forces is equal to 0. I can determine what the direction of the electric force is by saying it's going to be Q times the electric field. But this Q is negative, the electric field points up, so that says that the electric force points down. And so in order for this system to move through undeflected, my magnetic force needs to be opposite of the electric force. And so that's why I know that the electric force is, or sorry, why the magnetic force has to be pointing up. Okay? So I'll pause here to see if anybody has any questions about this one before I move on. Okay, so the next question follows in the same spirit as this one. And so in this case, I have some magnetic field that's going to be pointing out of the board. So I have a magnetic field represented like this. And just so this is 4x4, there's some symmetry here. This is my magnetic field. Sorry, I don't know if I said magnetic force. My magnetic field is pointing out like this. And we have some particle with some charge Q that's going to be moving with some velocity V, and this is going to be going up. So you're using the fact that you know that the particle is undeflected. Yes, that's ultimately how I'm saying undeflected means that the sum of the forces is equal to 0. That's what's meant there. So whatever electric force I have needs to be opposite of the magnetic force. Yeah. Okay. So this one, I give you what the magnetic field is. I give you what the velocity is and its direction. And I'm telling you that some charge Q. And what I want you to find here is two things. What direction this is going to precess in, and what the radius of precession is. And so what I can do is I can start by writing down the magnetic portion of the Lorentz Force Law. So that's just to say that FB is equal to QV cross B. And then use this to evaluate what the direction of the force is going to be. So fingers go in the direction of the velocity, and then I curl them into the direction of the magnetic field. And so when I do that, that's going to say that my force is going to be pointing this way. Okay, so this is the direction of my magnetic force. Now, what's going to happen here? If my force is this way, at some time later than this, this velocity is going to have to bend this way. And so later, my velocity is going to look like this. Okay? But now my velocities change, and so the direction of my force is going to change. So I can use the right-hand rule again and say this is the direction of my velocity. Curl in the direction of the magnetic field, my force is going to go this way. And then, again, it's going to go like this. And then like this. Okay? And so what we're seeing is this charge is going to be going around in a circle. Okay? Now, the second part of this question asks you to find what the radius of this circle is. Okay? So in order to do this, we're going to have to remember some kinematics from the last semester. And that's to say, when we have circular motion, what we can do is we can say that, well, in general, Newton's second law says the sum of the forces is equal to the mass times the acceleration. But this sum of forces is, this force is always going to be pointing into this circle, and it's going to be in the radial direction. So what I can say is that the force, or the sum of force in the radial direction is equal to the mass times the acceleration in the radial direction. And then we can remember from last semester for circular motion, the acceleration in the radial direction, a sub r, is just going to be minus v squared divided by r. Okay. So now that we have this equation here, what we can do is we can say that the sum of the forces in the radial direction is going to be equal to MAR, which is going to be equal to minus v squared divided by r. So this is always pointing towards the center of the circle. But when we do this FB is equal to QV cross B, this is also into the circle. So if I'm over on this side, this is a negative component here. So FB is really minus QVB. And so I can take this and I can plug it in here. And so this is minus this is minus mv squared. Minus mv squared divided by r is going to be equal to minus qvb. I can cancel a factor of the velocity, and then I can solve for what the radius is. I can get rid of my negative signs as well. And so what this says is that the radius is going to be equal to mv divided by qb. Okay. Oh, we're frozen. Yep, sorry about that. I had my fingers crossed this wouldn't happen today, and I need to figure out why OBS does this. Okay. All right, we're back. So I can see where it stopped working was right when I was writing this line. Okay, so just to go back through the part that it froze during, we wrote down what our centripetal acceleration is here. Okay, and we evaluated for that in this equation, so that's how I got down to this next line. And then I used the sum of forces, the left-hand side of Newton's law, to write down that this is equal to QVB. And then I just solved this equation here for the radius. Okay. This is what's called the cyclotron radius. And it's an interesting thing when you think about it, because with these parameters, I can do a very rough estimate of what magnetic field I need for the Large Hadron Collider. So we know, I don't know offhand what the, let's see. I'm just going to do a real back of the envelope calculation here, but I'm going to need the magnetic fields in Tesla. That's I think it's 14 Tesla. So if the velocity, so let's do an interesting calculation. We can see how close we get. If that's going to be relativistic, so it's probably not going to be very close. But let's say a Large Hadron Collider collides two protons together at a speed very close to the speed of light. So let's just say that this is the speed of light, which is in SI 3 times 10 to the 8. So 3 times 10 to the 8. I believe the magnetic field strength is 14 Tesla. So this is divided by 14 times the mass of a proton divided by the electric charge. So this is 1.6 times 10 to the negative 19 coulombs times, I just need the mass of the proton. I just need a mass of a proton. Proton mass is, this is 1.6 times 10 to the negative 27. So this is negative 19. This is going to cancel really nicely because this 8 makes this a 19. So all of my factors here go away. This is 1.6 divided by 1.6. 3 divided by 14. I might be off a little bit here, but I'm giving a rough estimate of the radius of the Large Hadron Collider to be. This is a factor of a half. This is if this was 1.5, that would be exactly 2. This is 0.2. I'm going to say that the radius of the Large Hadron Collider is about 0.2 kilometers. That sounds wrong though, and it's the relativistic portion of the calculation that's killing us here. So let's see, radius of Large Hadron Collider. I don't care about the circumference. I want to know what the radius. Okay, you're not going to give me the radius, but we can find out what the. So this is 26 kilometer. It's 26 kilometers. So 26 kilometer is equal to 2 pi r. So the radius is going to be 26 divided by 6, which is about 4. So I'm actually here's where relativity matters. What was I doing here? You guys might be like, he's just going off on some tangent. The way the Large Hadron Collider works is it accelerates particles up to a speed very close to the speed of light, and then collides them together. And so what I was doing was I was using this classical cyclotron radius in order to try to calculate what the radius of the Large Hadron Collider is. And you see actually that we're off by a factor of 50. So this is it should be about 4 kilometers, and I'm finding that it's about 0.2 kilometers using our classical approximation. But that's ultimately part of the reason for that is you're accelerating a massive particle very close to the speed of light. You need a lot more energy than just the magnetic field that we're approximating here. But it's actually, all things considered, 0.2 is not that far away from 4. There's a factor of 50, but Yeah. So that's kind of an interesting application of this this question that we have here, using the dreaded numbers. Okay. So let's see. The next question is going to be getting into what we're going to be getting a lot of practice with tomorrow in recitation, and this is what's called the Biot-Savart Law. So just to review very briefly what the Biot-Savart Law says and how it's really similar to the way that we found electric field from infinitesimal charges. So that was to say that dE is equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. This doesn't really have a name. If I wanted to, I can call this Wu's law, if I want to be cheeky. It really comes from Coulomb's law, but this equation itself doesn't have a name. What we're going to be using right now is what's called, it does have a name, it's called the Biot-Savart Law. And this says mu naught divided by 4 pi times I dl cross r hat divided by r squared is equal to the infinitesimal magnetic field. And so this equation allowed us to calculate what the electric field is from some infinitesimal charge. This equation allows us to find what the magnetic field is from some infinitesimal little piece of current. Okay, so the problem that I had here was I said you have some circle of radius A. So this has some radius of A, and it has some current that goes around the loop in a clockwise direction. So the current is going to go this way. And what we want to do is we want to calculate what the magnetic field is at the center. Okay. So in order to do this, let's define what dl is. So dl vector is going to be equal to a d theta times theta hat, where this theta hat is just going to be telling me that I'm going in the same direction as the current. So dl contains the directional information for the current. You see, the current's just it's just a scalar quantity. It's just I. But dl is really what's carrying the vector information. It says like where the current is going and in what direction. So that's dl. So we've defined dl. Now r hat by definition always points from the infinitesimal that we have to the point where I'm trying to observe the field. So this is going to be pointing in like this. And so if I look at the angle between dl and r hat, for everywhere on this arc of the circle, it's actually just 90 degrees. And so what that allows me to do is to say that dl vector cross r hat is going to be equal to just the magnitude of these two vectors times the sine of the angle between them, which we know is going to be 90 degrees, times the unit normal vector that's mutually perpendicular to these two by applying the right-hand rule. And so that says that this is a d theta times our n hat. Now to find n hat, all we need to do is we need to point our fingers in the direction of dl and then curl them into the direction of r hat. And that's going to say that here this is going to be pointing into the board. So this is a d theta times some vector that goes into the board. Okay. So that takes care of almost everything. The last thing we need is just what the radius is. Well, we're given here that the radius is r, and that's the same for every dl around the arc of the circle. So we're ready to put this together to find what the magnetic field is at the center. So this is going to say this is mu naught I divided by 4 pi times the integral of a d theta divided by a squared times a vector that's going to be pointing into the page. And this integral for theta starts at 0 and goes all the way around the circle. So this goes from 0 to 2 pi. Okay? So this is a pretty nice integral to evaluate. It's just the integral of a constant. So the integral of d theta from 0 to 2 pi is just going to be 2 pi. That 2 pi is going to cancel with a portion of this 4 pi that we have here. So we're left with a factor of 2 in the denominator. And so this just says that this magnetic field B is going to be equal to 2 times A in the denominator with a mu naught I in the numerator times the vector that's going to be pointing in. Okay. Is r hat just left as a vector, or do you need to know the magnitude of it? So r hat's a unit vector, right? So the magnitude of this is always 1. Yeah. So I implicitly have that here, so this is times the magnitude of r hat. But because it's a unit vector, and it's part of the reason why we like to work with unit vectors, because a lot of times you end up having these situations where I have a dot product between two unit vectors. That's either going to be 0 or 1 depending on what the unit vectors are. Here I have a cross product with a unit vector. So whatever magnitude that comes out of this is just going to be 1. So that's where that went. Okay. I think that's about it for this one. Now the one that I gave you guys in the homework, it's not going to be this easy, but it follows very naturally from what I actually did in the notes. So in the notes I did the infinite line. And I used this, this is dl, this was what I called y, this is x, r is equal to the square root of x squared plus y squared, and then this is the unit vector r hat. And then when I integrated this, this goes from negative infinity to infinity. In the homework, you just have this square. So think about, and I'm not going to tell you exactly what the answer is, but think about what's different between the example that I did in the notes and the homework. And you should be able to do that really easily. Now the other thing is that there's a little bit of symmetry that you can exploit here. So you don't have to do the integral 4 times. In fact, a good question, if I was feeling like a jerk on the exam, would be to give you a hexagon. So you have some electric field that goes, or some current that goes around the hexagon. Find the electric field at the center. You can, again, you don't have to evaluate 6 integrals. You only really need to evaluate 1, because all the sides are really the same. And if we wanted to keep going with this, so we could start with this is me just mathing. So start from a triangle, then go to a square, then go to a pentagon, then this, then a 7-sided polynomial, which I can't draw that well, then an octagon, and then keep this pattern going. So you go here to here to here to here to some polynomial with n sides that looks like a circle. And what would be interesting to show is find the pattern for what the magnetic field looks like for every one of these. And then if you see what that pattern is for any n-sided polynomial as n approaches infinity, you'll find that the magnetic field is actually going to be the same as the one that we just calculated when we said it was actually a circle. That would be an interesting question. Not one that I would ask on an exam for us, but a junior level course. Someday, if they ever let me teach a junior level course, then that would be a really good question. Because it makes you think about series and sequences in a way that you can actually think about some physics that's actually coming out of it. Okay, so enough with my infatuation with mathematics. Let's talk about in the last oh, it was half an hour, so I might not have an hour worth of material today. So in the second half of the stream, what I want to do is I want to talk about Amperes Law and some of the things that we'll see on Wednesday. So you might look at this these equations that we have. So I'll go back to writing this infinitesimal electric field here, and then say if I arrange these in a particular way, the equations are really begging for a fourth equation here. So this is I dl cross r hat divided by r squared. And then we had Gauss's law. Integral E dot ds is equal to q in divided by epsilon naught. So this was how we could calculate an electric field. Here's how we can calculate a magnetic field. This is brute force, brute force. And then this is symmetry. Right? So we have this nice table that we could draw here. And the physics is really begging for one more equation. Some way that we can calculate magnetic fields using some type of symmetry argument. And the equation that fits in this box here is what's called Amperes Law. So what Amperes Law says is the integral around some closed loop of B dot dl, well, so much for that piece of chalk, is equal to mu naught times I in. Okay. So when we look at this, in a way, it kind of looks similar to Gauss's law. We have some sum of field over some closed thing is equal to something inside that. And that's put very vaguely, but I'll explain more what I mean by that. So when we think about Gauss's law, say I had some I'm already drawing my Gaussian surface. Say I have some infinite line charge density like this, and I want to find what the electric field is that points radially away from this at some radius of r. We could apply our brute force technique and find all the little pieces of dq and then the unit vectors that point away from them and sum and find what the electric field is here. Or we found we could apply Gauss's law, which actually gives us a much easier way to go about this. And that's to say, if I define some Gaussian surface so that when I do the integral of E dot ds, this reduces to E times s, then this is just going to be equal to the charge that's inside of this Gaussian cylinder. This is some length of L, divided by epsilon naught. And so the charge inside this Gaussian cylinder is just going to be lambda times L divided by epsilon naught. S is going to be 2 pi RL. And so this is going to be, my electric field here is going to be E is equal to lambda divided by 2 pi R times epsilon naught. And in 1, 2, 3 lines, we were able to do a calculation that had we tried to do this in terms of the infinitesimal charge, it would probably be more like, if you're good and you can do a lot of the algebraic steps in your head, maybe like 10 lines. If you write out every step and you end up with an integral that you need to do a trig substitution, it could be a whole page to do this in terms of the infinitesimal. We're going to see something very similar with this. So in the notes, I was lazy and I wrote it in 3 lines for how I can find what the magnetic field is from the infinite current. So in the notes I applied the Biot-Savart Law in order to do this, and truth be told, I didn't do the integral when I wrote that. What I did was I knew what the answer should be because I knew how to apply Amperes Law. And so that's what I'm going to show you now. So you could do this with the brute force way, but we're going to see how we can do this with the symmetry way. So to come back to what we had here, Gauss's law says draw some Gaussian surface. Amperes law says draw some Amperian loop. And so the reason ultimately why you have a surface for Gauss's law is because you have this ds. This is an infinitesimal surface element. The reason why you have a loop for for Ampere's law is you have this dl. And this dl is some infinitesimal length, the same that we've seen in plenty of other places. So what that says is draw some loop that goes around the current, and whatever current goes through that loop is going to be equal to the sum of the magnetic field along the loop. Okay? So what I'm going to do here is I'm going to draw some circular loop that goes around here. And I'm going to give this a very particular direction. I'm going to say that it's going to go around like this. So when I do that, and the reason why I'm doing this is because I actually already know that a magnetic field should go around a loop of wire this way. So when I do that, just in the same way that with Gauss's law, if I had the right surface, this integral reduces. Now that I have the right loop here, this integral reduces. So integral b vector dot dl is going to become the integral of b times dl. B is going to have the same value every point on this loop, which means I can pull it outside the integral. B integral dl. And the integral of dl is just going to be the total length of the loop. And here, this is just some circle with radius of r. And so the total length of the loop is just the circumference. And so this is b times 2 pi r. Okay? So that's just the circumference of this circle. So it's b times 2 pi r. Now, in order to find what this magnetic field is by using Ampere's law, I just have to ask myself, what's the current that goes through the loop? The current that goes through this loop, that passes through the area that's enclosed by the loop, is just the current I. And so this is going to be equal to mu naught I. And so this says B vector is going to be equal to mu naught I divided by 2 pi r times theta hat, where theta hat is how I'm defining the direction that this loop is going around. Okay. Now, I did something here that I swept under the rug a little bit that you guys might worry about. I chose a direction that this loop is going to go around. I said it's going around like this. It could have gone around like this. You know, I had a choice of which way I wanted to go. And there was a very particular reason why I chose it to go around the way that I did. And that's going to come down to another form of the right-hand rule. And that's to say, if I have some current going in this direction, the direction the magnetic field is going to follow the right-hand rule according to, if I point my thumb in the direction of the current, the magnetic field curls around the wire in the direction of the way that my fingers are going to curl. So thumb in the direction of the current, magnetic field curls around this way. And so that's why I drew the loop to go around the direction that I did. Okay. Let me see. Is there anything else I want to say about this? Not really. Now, the other thing, yeah, there's something else that I could say. So this is just some current I that's in some really tiny wire. But what I could do to make this problem a little bit more interesting is I could say, what happens if I have some thick wire? And I want to find the magnetic field everywhere. If this has some radius of A, and this has some radius of A, and I want to find the current everywhere, that means, the magnetic field everywhere, that means there are two regions that I need. I need R is less than A and R is greater than A. Okay? And I'm going to have two Amperian loops. So if this is the current that's going in this direction, one of my Amperian loops is going to look like this. The other one is going to look like that. Okay? So let's look at how we can evaluate the first region, because that's the second region is actually the same as what I just did. Ooh. Make a nice chalk spot on the floor here. I'm going to have to vacuum later. So in this region R is less than A, we see that we're not enclosing the whole current. It's some proportion of the total current. And the way that we can figure out what that current is actually to go back to an equation that we've already used. And that's to say that the current is equal to the flux of the current density vector. Are we going to need to use a loop other than a smoke ring? I haven't decided yet. Probably not, because we're running short of time for the semester. There are other loops that you could do. So for instance, for a solenoid. For a solenoid, this is the loop that I would choose. We don't really have time to do all of the symmetries of Amperes Law, unfortunately. So we're going to constrain ourselves only to, as you say, the smoke ring that we have here. Yeah. There's another interesting one that also ends up being a ring, but it's for a torus. So imagine this is, I'm actually pleasantly surprised at how well that came out. This is just, it's like a donut. You can find what the magnetic field is inside the donut if you wrap a solenoid around itself, and then that's the Amperian loop that you have. Again, we're not going to really have time for that. Okay, so let's come back to this one right here. So for the Amperian loop that I have here, just again like Gauss's law, this has some radius of r, right? It's not going to enclose the whole current. It's only some small amount of the current. And in order to find what the total current is, we need to evaluate what this integral is. But we don't know what J is. This is kind of like when we were doing insulators, and we wanted to say that Q in is equal to the integral of rho dV. We needed to find what rho was. Here we need to find what J is. So in order to find J, again to go back to this, if we had to find what the charge density is, we said that rho was equal to the total charge divided by the total volume. Same idea here. J is just going to be equal to the total current divided by the total area. Okay. And that's to say here I have some current I, and the total area is the cross-sectional area pi a squared. And so this J is going to be I divided by pi a squared. So that's what J is. Now, we want to, let me write down Amperes Law again. So integral B dot dl is equal to mu naught times I in, right? We want to figure out what I in is. The left-hand side is actually the same as I had before. If I'm only going to do the Amperian smoke rings, as you say here, this is always going to be B2 pi times R. That's always going to be the case for us. But be cognizant of the fact that it doesn't have to be. It's just, in our case, it will be. And I'm thinking of questions that I could still ask where it's not true. So when I say something's always true, you shouldn't trust me. But when we have this type of symmetry, the loop that I'm going around is just a circle, and so the total length of that circle is going to be the 2 pi r. And this is equal to mu naught times I in. So this comes back to what I was talking about over here. I want to find I in. This is equal to the integral of J dot dA. J is just going to be this constant. We can pull that outside the integral. I divided by pi a squared. Times the integral. dA is really just going to be, this is going to be 2 pi r dr. Okay. And now we need to evaluate our limits of integration. And this is the important part that, again, harkens kind of back to what we were doing with Gauss's law for insulators. So remember when we did, if this was some charge distribution, this is some radius of r. We want to find the charge inside of this region. When we evaluate the limits of integration, they go from 0 to r. Same case here. This goes from 0 to r. Because the Amperian loop on the inside doesn't have all of the current passing through it. It's only the current that goes up to this radius of r. And so what that says is this goes from 0 to r, so I can evaluate my integral. My pi's are going to cancel. I'm going to cancel a factor of 2. And this says that I in is going to be I r squared divided by a squared. Okay. So then I can take this I in and plug it in here and just solve for my b. And so b vector is going to be equal to mu naught times I times r divided by 2 pi a squared in the theta hat direction. And that's it. Okay. So not a lot else to say now. How could I? What's something else that I could do? Well, again, you'll see me coming back to Gauss's law a lot because I really want you guys to connect the idea of symmetry and the ways that we're evaluating in Gauss's law what Qn is and in Amperes law what In is. What was a trick that I could play here to make a different problem? Well, I could make this hollow, right? I could say this is now some insulating shell. And so what is this going to change? Well, if this is some radius of A, then I'm integrating from A to R. I could do the same thing here. So now I'm going to have my current going like this. And my limits of integration when I draw my Amperian loop are going to go from this inner radius. I had it A here. Let me call this, well, let's call this A and call this B now. This one goes from A to R. The second one goes from A to B. What's something else that I could do? Well, I could give you some current density that varies over the radius, right? I could do that here with this problem. I could say that rho is a function of R is equal to rho 0, R cubed over A cubed. I could tell you that J as a function of R is going to be equal to J0 times J0 R divided by A times X hat. Right? So I can give you some current density that varies as a radius. What's something else that I can do? Well, with our Gauss's law problems, we could have multiple charge density. So I could put another shell around this. So I had rho as a function of R here and then make this one a constant, rho 1. I can do the same thing here. Have one charge density in here, a second charge density here. A lot of, and this is why the Gauss's, I don't always realize it, and I don't always remember until I get to doing Amperes law. How much of the Gauss's law tricks, if you want to call them, that I might play really carry over to Amperes law. Basically all of them, except for the symmetries. So in a way this is a little bit easier because I can't do something with spherical symmetry. That would be very difficult to do to think about a way that I could draw a loop in spherical symmetry and have that be the same translationally. In fact, it's impossible. You can't do that for spherical symmetry. Other things. What else do I want to say about this? I think that's about it. So we're going to be doing in recitation problems with the Biot-Savart Law. So that's one I could tell you some of the tricks that I could play with that one. So we've already done with Biot-Savart. We've already done the circle, and after the homework we would have done the box. There's not really anything else I can do other than these two shapes. It's just a matter of how do I use the shapes. So I could do something like that. So this is going to be some angle. This is going to change what my limits of integration are. It's one part circle, one part line. I could do something like this. This is actually one of the problems that we're going to do tomorrow, where I have these three segments. But really, it always just comes down to these two shapes and then how you define your limits of integration. And I'm gonna be try to be clever to come up with something interesting for you guys to solve. But offhand, it's actually kind of limited what things I can do and play with arcs of circles and straight lines for Ampere's law. There is a way that I could ask you an elliptical problem. But I don't know that I would want to do that because I don't need you guys coming to my office with tar and feather and pitchforks and torches. But there is a way that I could say if I had two currents here, call this I1 and this is a minus I1, and make this elliptical, that I could say that find what this is. Evaluate the integral of B dot dl. And the thing here is you don't explicitly evaluate the left-hand side. You evaluate the right-hand side. Because if this is, call this I, and well, it doesn't have to be. This could be I1 and minus I2. It's very difficult to evaluate what the left-hand side is, because what that means is I need to find what the components of the magnetic field are at every point here, and then take the dot product with the path along that entire thing and then add it up the whole way. But what's easy is to say, I have some loop that I drew here. What current's on the inside of it? Well, it's just the sum of the current in here. So it's going to be I1 minus I2. So integral B dot dl, in this case, is just mu naught times I1 minus I2. That's a trick that I could play. And you could do that for whatever geometry you want, as long as I'm enclosing both of these. So I could make some weird shape that goes around this, evaluate the integral of B dot dl around that shape, and it's just going to be the mu naught times the sum of the currents that go through it. Where I'm going to have more of an opportunity to be clever in asking you guys interesting questions is when we get to Faraday's law. Faraday's law, there's a lot of room for me to play with. But that's pretty much it. So unless if there are any questions about what I did here, that'll be it for the live stream. I'll post this and also the, I have a lot of things to post, so I'll post this right after this. I'll post the lecture from today, and then I'll also post the solutions to the exam now that everybody's taken the makeup exam. Okay, so that's going to be it. I'll see you guys tomorrow.